Does it work? Oh, okay. Wonderful. This was a critical moment. So you can really see my...
Yes. Yes.
White writings on the black phone.
Pardon?
White writings on the black list of paper.
Why I choose black?
The text is
well, because
white.
it's a blackboard.
Yes.
Okay.
Okay, so let's wait 1 more minute until it's 10 o'clock. Okay, so it's 10 o'clock. So I say welcome again to the participants who have joined us right now. So it's our second lecture this, well, where I live it's morning, but maybe not for everybody. It's the second lecture today, and the lecture will be given by Wolfgang Arendt about continuous kernels for positive semigroups, applications to boundary value problems and semilinear equations. Wolfgang, please have fun.
Well, thank you very much. Thank you for the introduction, and thank you for the invitation to Nizhny Novgorod. Unfortunately, only virtually. Okay, my talk will be on semigroups on spaces of continuous functions, and actually it will be C omega bar. So it will be not directly boundary conditions, but different boundary conditions. I mean, Aubin in particular. Let me give you just one reason. There are many reasons why this space is of interest. For instance, the probabilists like it very much because you can get processes from positive semigroups on C omega bar. But there are many other reasons. Here I want to mention just one reason I like very much. We have a generator, or minus A is the generator of a semigroup. I will always use minus in this talk. You will see why. And we are interested in considering the semilinear problem. So we are considering this semilinear problem. And G is just composition by a function, like in many examples. So we have G, a locally Lipschitz function, locally Lipschitz continuous function. And then C omega bar is a nice space because the composition by G defines a mapping, a nonlinear mapping from C omega bar to C omega bar, which again is locally Lipschitz on this space. Whereas if you consider instead of C omega bar LP, then it is never locally Lipschitz unless the function is already globally Lipschitz. So if you want to consider locally Lipschitz perturbations, and then this is a good space. So this is one of the reasons why C omega bar is nice, and many other reasons. For instance, the norm is very strong and gives us uniform convergence. This is also a nice aspect. Today, I will give you three examples of, or three classes of examples of semigroups on this space. It is actual research, C omega bar. Here I wanted to tell you a little story, but history, but maybe I skip this and I recall the Danville-Pettus criterion. Well, many people call it the Danville-Pettus criterion. It says the following. if we have an operator on L2, so I always will start by an operator on L2 because this is maybe the easiest to define a semigroup in many cases, because we have Lax-Milgram, and then it is quite easy that, for instance, an elliptic operator defines a semigroup on L2. But we want more, and one we ask ourselves, when does this operator come from a kernel? So two things are equivalent. We have a kernel in L infinity, so Tf of x is equal to this integral kxy f of y almost everywhere. And well, the norm from L1 to L infinity, so it's only defined for functions in L2, but this norm here is finite. So this is equivalent. Oh, I forgot to say it is finite. So this norm is finite. These two are equivalent. And well, actually this theorem, I learned this from Alexander Bukwalov, is actually due to Kantorovich-Wulik, who published it in 37. I did some joint work with Bukwalov when he was visiting France. We studied the holomorphic dependence of kernels. So if the operator is holomorphic dependent, one can show that, or one can choose kernels which are holomorphic, but that's not so obvious to see. This was a work we had done. I don't remember exactly the year, but when Bukwalov came to France, he came from Leningrad, and 3 months later, when he went back to St. Petersburg. So you will be able to figure out which year it was exactly. Anyway, this the question we asked ourselves more recently is, when is this kernel continuous? When do we have a continuous kernel on omega bar cross omega bar? And here's the question. Let omega be open and bounded, and later it will be connected. So this is for all the talk today. Omega is in RD, an open, bounded, and connected set. Connectedness is not important in this moment, but later. And we are given an operator from L2 to L2, a linear mapping, and then we say T has a continuous kernel if there's K, which is now defined on omega bar cross omega bar and continuous, such that Tf of x is given by this kernel. Now, the problem is how to find out whether an operator has a continuous kernel. One consequence is that TL2 maps T maps L2 into C omega bar. But this is not sufficient to ensure that there's a continuous kernel. The right property is the following. Let's assume that T is self-adjoint, but this is for simplicity. One can change things to arbitrary operators, but in my talk, I will talk about self-adjoint operators today, only self-adjoint operators. So if T has this mapping property, L2 is mapped by T into C of omega bar, then T power 3 has a continuous kernel. And the power 3 is optimal. It's not true for T power 2. In particular, if you think about the Kantorovich-Wulik theorem, it will not be enough that T maps L1 into C omega bar, what one could think. This does not lead to a continuous kernel in general. But anyway, we are interested in semigroups on this conference, so the power does not matter so much. The setting I like, and I want to choose here in this talk, is semigroups which have this property of C omega bar smoothing. Okay, so we assume we have given a semigroup on L2, which is self-adjoint. The generator is minus A, so A is also a self-adjoint operator. And then we say that the semigroup is C omega bar smoothing if two properties are true. So the first one, A, is it maps L2 into C omega for each T positive. And the second is the restriction to C omega bar is a C0 semigroup. This is a quite severe restriction and needs proofs in the examples I will give you, and sometimes difficult proofs. Then we have several consequences, and I will talk about these consequences now. Well, first of all, T of T is a compact operator on L2. I mean, it is even a Hilbert-Schmidt operator on L2. Then we know TT has a continuous kernel, and here's a proof. I mean, for the semigroup, since TT is T over 3 power 3, the theorem works, and we get each TT has a continuous kernel on omega bar cross omega bar. Okay, so the property I'm interested in now in the following is this property of positivity improving. And this is actually based on two papers. Well, one paper is joined with Tomter-Elst, and this will concern mainly the Dirichlet to Neumann operator as an application about which I will speak a little bit later. This will be my second example. But this property has been studied. Now I talk about it in a self-adjoint context, but in the non-self-adjoint context, we have a joint paper together with Jochen Glück and Tomter-Elst, where we study this property of positivity improving. So T is a semigroup, again, on L2 of omega. And we say this semigroup is positive if each TT is a positive operator. Now, this is ambiguous on Hilbert spaces, but it's in the lattice sense. So if F is positive almost everywhere, larger or equal than 0 almost everywhere, then TTF is larger or equal than 0 almost everywhere. So this is the definition. Now we say, now the theorem which I want to present is the following. If omega is bounded, open, and connected, now connected is important. If T is positive, self-adjoint, and the main hypothesis is C omega bar smoothing, well, then it improves positivity in the following sense. If F is larger or equal than 0 in L2, different from 0, not 0 almost everywhere, then TTF of x is larger than 0 for all x in omega bar. So omega bar is a compact set. So actually TTF is larger or equal than some delta larger than 0. And the delta depends on T and on F. Okay, so this, I call it the positivity improving theorem. So this is it's a consequence of having a kernel. We use the kernel to prove this. Okay, there is another context. This is in this paper joined with Jochen Glück, but here in the self-adjoint case, we use the kernel to prove this theorem. Okay, let's call this the positivity improving theorem. So we need a semigroup which is positive and which is C omega bar smoothing, then it is automatically positivity improving. And this has interesting consequences, and here is the first consequence. I will now present you 4 consequences of this theorem. So here's the first one. It is a theorem about the strict positivity of the principal eigenvector. Now, minus A is the generator of A. So the context of the following is exactly the context of theorem 2. So we have a C-series semigroup, which is positive, and which is the omega bar smoothing, and so it is positivity improving. So in this, the consequence is, well, the operator A has compact resolvent because each TT is compact. So there's an orthonormal basis of eigenvectors, and the eigenvalues are lambda 1, lambda 2, etc., and they go to infinity. So lambda 1 is the first eigenvalue of A, and this is the reason of the choice of the sign of A. We like eigenvalues going to infinity. Okay, then for the first eigenvalue, lambda 1, there is a unique eigenfunction of norm 1, which is larger or equal than 0. And this is the Kreil-Gutmann theorem. This is well known. But what we get now is that this eigenfunction is larger or equal than delta for some delta. It's a strict positive eigenfunction. And this is a property which has interesting consequences and which was not known for some of the examples I will give you. I should also mention here, lambda 1 is the only eigenvalue with a positive eigenfunction. So whenever you have an eigenvalue with a positive eigenfunction, then it is lambda 1, and the eigenfunction is unique up to normalization, and it is strictly positive, larger or equal than some delta. Okay, this is the first consequence I want to tell you. Then my second point, we can perturb this semigroup. So again, while I go back just to be sure that we know where we are, we have a positive semigroup. It is C omega bar smoothing, and it is self-adjoint. Okay. So we know it is positivity improving. Now, here's a perturbation result. Whenever m is a function in L infinity of omega, then we look at the perturbed operator, and this again generates a semigroup which is positive. This is obvious. It's self-adjoint. This is obvious also, but it is also C omega bar smoothing, even though m is only in L infinity. Well, this is not so difficult to see, but the positivity improving property has an interesting monotonicity result. If m is smaller or equal than m2, but different, then the first eigenvalue is strictly positive, is strictly increasing. So the first eigenvalue is strictly increasing as a function of m, of the perturbation m. So if we have m1 is smaller or equal than m2, and if the two eigenvalues, the first eigenvalues coincide, then already m1 is equal to m2. This is an irreducibility argument. Many of you will know maybe, but this is true also in this context. Okay, I will come back to this consequence. This is the second consequence I want to mention. The third one concerns the elliptic semilinear problem. Okay, so again, my semigroup is this self-adjoint positive semigroup, which is C omega bar smoothing, and minus A is a generator. A is a self-adjoint operator with compact resolvent. So as example, I take logistic growth as an example, but it can be generalized to other semilinear functions. So the following are equivalent. The first eigenvalue is smaller than 1, and we have a solution of AU equal to U times u1 minus u. And this solution is in the domain of the operator, but it will be automatically even in C omega bar. And if it is positive, larger or equal than 0, non-zero, of course, then it is also automatically larger or equal than a delta. This is not the same delta as before, just some delta. This is some work with Danedanas, but let me tell you how this condition lambda 1 smaller or equal comes in. Maybe I tell you this part of the proof. So the proof is from 2 to 1. Okay, so I assume I have a solution, and then the eigenvalue has to be smaller than 1. Why? Okay, we have AU is U times 1 minus U, or I can say A minus UU is equal to U. And now the U is a multiplication operator. U is a bounded function. It's in C omega bar, but bounded would suffice. So, but what I said, the 1 is an eigenvalue for A minus U, but it's an eigenvalue with a positive eigenfunction. So lambda 1 of A minus U is 1. But by the strict monotonicity, this is larger than lambda 1 of A. So if there's no U, okay, so lambda 1 is smaller than A. Maybe I tell you just a word about how to prove things how to prove the other direction, I mean the existence. And this is existence, well, for people who work in semilinear problems, in such a context, they have a reflex, they use some iteration. They use some fixed point theorem, and what one needs is one needs an okay. So one needs pardon?
Я микрофон включен.
У меня нет.
А ты обедать собираешься?
Irina Melnikova, can you please switch off your microphone?
You don't understand very well. Is it better now?
Okay, it's okay, Wolfgang. Just go ahead. Everything's fine.
Okay, so what we need is a sub solution. Sub solution. We need a sub solution, and we need the super solution. And then there are, this was the super solution. And then you can just iterate this equation and it converges. Okay, it needs some argument. And now, how do we get a sub-solution, a super solution? So we may choose epsilon u1, and we may choose C u1 for C large enough and for epsilon small enough. And here, for the C large enough, we need that lambda 1 is smaller than 1. And then one obtains sub-solutions and super solutions. And then, then it is for people working in sublinear theory, it's somehow a routine to obtain a solution. Okay, so here for the C, we need that U1 is larger or equal than delta, and we need also that lambda 1 is smaller than 1. This is important to get this property. Now, we can also, and this is my last application of the theoretical part, say, so again, we have this semigroup, which is positive C omega bars smoothing. So we know it is even positivity improving. And then we can also solve the semilinear problem, which I have also the semilinear problem. we can solve this semilinear problem. And we even get a dynamical system, and we can say something about the asymptotic. So this is the parabolic case. Now, my main point maybe is to give you examples. Now, the first example is Robin boundary conditions. We assume that omega now is, again, open, bounded, connected, and with Lipschitz boundary. And such a thing we call a Lipschitz domain. So bounded, open, connected, and Lipschitz boundary. Then I recall you, if we have a Lipschitz boundary, then we have a trace. So there exists a bounded operator from H1 to L2 of the boundary, L2 of the boundary with the surface measure, such that for functions which are continuous up to the boundary, it's just a restriction. And this has an extension, and this extension we call the trace. Now, we are given an operator beta in L infinity of the boundary, and then we define the Laplacian delta beta, so this is the Laplacian with Robin boundary condition defined by beta. The domain consists of all u in H1, the Laplacian is in L2, and then at the boundary we have the normal derivative plus beta u, so this should be the trace of u here. This is the u, I don't say this is a trace of u. Beta, the trace of u, is equal to 0. And the normal derivative is defined in a weak sense. And then Laplacian beta u is equal to u. Okay, this operator is a self-adjoint operator. This is not difficult to prove. It's a self-adjoint operator on L2. But what is difficult to prove is that it generates a holomorphic positive semigroup, which is C0 smoothing on L2. And this is actually, this was a result of Robenitka, who was a student in Ulm, and this was his thesis. So such boundary conditions, of course, have been considered before. Newton, it should be, we should quote Newton, who invented this boundary condition, but Gustav Robin became known for these boundary conditions. Okay, in the smooth case, such a theorem was known. I mean, this is in the context of Stewart and Masuda method. But in this general situation where we just have a Lipschitz boundary, this theorem is new and remarkable, I think. And well, let me just give you, I want to say something about the trick. There is a trick to treat such boundary conditions. So you see, what you have to do is, if you have a solution of lambda u minus delta u equal to f, and say f is in C omega bar, I mean, you have to prove the range condition. You have to prove that u is continuous. I mean, this is not, I mean, by no means obvious why u is continuous up the boundary. And this is the trick. I mean, I learned the trick from Carlos Koenig, and but people like Masia also, they know this trick, but actually I don't know a reference. And then Robenitka, he did a very nice work on it. So what you do is the following. You have omega is your Lipschitz domain. And then if you have such a solution, this solution exists and is in H1. But you reflect it along the graph. Well, this is not you reflect it along the graph. I mean, not so reflect it in this way. This is a reflection. And then it becomes a solution of an elliptic equation. When you reflect u and you extend it here, reflection along the graph, the new function is a solution of an elliptic equation. And in the elliptic equation, the parametrization of the boundary comes in as coefficients. These are coefficients which are merely in L infinity, because the normal is just in L infinity. But then we have the Georgi-Nash. The Georgi-Nash gives us that this new function u, I mean u and u tilde, is continuous. I mean, this is the idea of the proof, and still it's technical to work this out, and it's a very nice work of Gorbinica, and is published in the Journal of Differential Equation. Okay, so we know this function is this semigroup is even C omega bar smoothing. There's a misprint. This is very nice. I can correct misprints. It's C omega bar smoothing. And so we know it is positivity improving, and we know now the first eigenfunction is strictly positive. And this was not known before, because what did people do? I mean, all these people working semilinear problems, they used the Hopf maximum principle to prove this. There's this Hopf maximum principle, and this is just C2 domains. I mean, it's just definitely not possible for more general. So C2 or C infinity. So this, in the Lipschitz case, this is a new result. Okay, now my second example, and this is again a class of examples, is a Dirichlet-Neumann operator. Now, let me tell you what this is. Omega is a Lipschitz domain as before, and M is in L infinity of the interior of omega. And now one defines an operator, dm, this is a Dirichlet-Neumann operator on L2 of the boundary. So this is an operator which is defined on the boundary. The domain consists, okay, of all G, which are, there's again a misprint, which is a really misleading. I'm sorry. So it's L2, it is L2, it's just a function in L2 of the boundary. Now, what do? We take this function and we solve the Dirichlet problem. So we solve the Dirichlet problem. We choose a function u, which is defined on omega. It's H1, and it satisfies this equation in distributional sense. And the trace of u is G. So this is a solution of the Dirichlet problem. And then we ask that the normal derivative is in L2. And then we define the m of u is the normal derivative. And again, a misprint. I'm very sorry, I read it so often. So dmg of this g is the normal derivative of this u. There's a problem of uniqueness. In general, this is merely a graph, a self-adjoint graph. But if we assume that the Dirichlet Laplacian with this m perturbation has not zero in the spectrum, then it is a self-adjoint operator. So let us assume this condition u. Let us assume that this here is well satisfied. So the only solution of this problem, which has boundary 0, is u equal to 0. So this is just a spectral condition. This operator, the Laplacian, has discrete spectrum. So you may just be, so just a spectral condition. Okay, then this operator is self-adjoint and bounded below. So we did a lot of work on this Dirichlet-Neumann operator, and this was a paper where we used a method of hidden compactness to prove such thing. Now I deviate from my subject a little bit, because I want to tell you that this Dirichlet-Neumann operator became famous by the Calderon problem. Because Well, Calderón in 1940 worked in the Argentinian oil company, and there he encountered the problem, and they wanted to look for oil. And there is this method of electrical impedance method. So electrical impedance tomography is also used in medicine, and it is used for finding oil. And in Auckland, there's a thesis where they want to use it for finding gold even. So it's interesting. And well, you put some voltage at the exterior, and then you measure the current coming out, and then you want to deduce the electrical conductivity in the interior. So you look for the electrical conductivity in the interior. But this is up to some transformation exactly what the Dirichlet to Neumann operator does. The M is the conductivity in the interior, well, up to transformation, which is bijective. So the M is the conductivity. And this problem was solved in 1987 by a famous paper by Sylvester and Ullmann. And here I refer to a theorem, which is in a paper from 2014. And it says exactly, if M1, M2 are in L infinity, the Dirichlet to Neumann graphs are equal, then M1 is equal to M2. It says exactly this. And you don't need this uniqueness hypothesis. It's always true. But then here you have graphs, and only if you have the uniqueness hypothesis, you have real self-adjoint operators, which are bounded below. Okay, now let's look. What did we do? So we let us assume that M is larger or equal than 0. This can be generalized, and let us assume that U is verified. Then we know already dm is an operator. We know already this operator is self-adjoint and bounded below, and we prove that it is that it has this property, and also that the restriction is a C0 semigroup. So in other words, it is C delta omega smoothing. The context is a little bit different now, because delta omega is a closed subset of delta. Delta omega is now a closed set. It's not in RD. But anyway, I mean, exactly the same is true. And this is not obvious at all. I mean, while the work of Robinitka gives, this is elliptic regularity, the first condition is basically done, but that it is a C0 semigroup, this is extremely difficult to prove, because you see the normal derivative is only measurable. And now you have to prove that the part of the operator has dense domain in C delta omega, and this is difficult. We worked quite a lot of time until we found a solution. Okay, and so this semigroup is positivity improving, and here I recall what this means. It's positivity improving. Now, this positivity improving is surprising, because I did not suppose that gamma, that the boundary is connected. I suppose only that omega is connected. And here's an example. I mean, take a ring or something like this, then the boundary has two parts. There's one part and one part. And even if you start by a function which lives only here and is 0 on the outer ring, the semigroup applied to this function lives everywhere. So this is surprising. So this is positivity improving. Well, this result is new. I mean, what was known before, if omega is C infinity, then Escher, he proved that we have a holomorphic semigroup, and he used this Masuda-Stewart method to prove this. Here's an application, here's a corollary. If M1 is smaller than M2, and if M1 and if M2 are both in L infinity, and if the first eigenvalue of the Dirichlet to Neumann operator, so this is the first eigenvalue outside on L2 of gamma, on L2 of the boundary, if the two eigenvalues are the same, then M1 is equal to M2. So it's the solution of an inverse problem, or the Calderon problem, in a very particular context, of course. I don't think that you can find gold with this corollary, but here's a proof. M1 is smaller or equal than M2, so one can prove that the semigroups verify this inequality. And then this irreducibility, or which is the same as positivity improving, implies that dm1 is equal to dm2. And now we use the result by Ullmann and Silvestre and obtain that m1 is equal to m2. So our hypothesis is purely on the boundary, and our conclusion is then this. But of course, this link is just a semigroup link, but it's also interesting. We use a semigroup to prove an elliptic result. I mean, it's we go via the parabolic equation. Now, my third example, and my last example, it's a little bit different, since now I don't know anything about a semigroup on L2. So it will be just a semigroup on C omega bar. So you see here, it's non-local Robin boundary conditions. So I learned from Professor Skubajev the first time about local boundary conditions. And here, well, some 2 years or 3 years ago, we studied these Robin boundary conditions, non-local Robin boundary conditions. Here I explain you how they are defined. Again, omega is a Lipschitz domain, and again, beta is an L infinity of the boundary. And now the non-local boundary conditions are given by a function which is defined only on the boundary. And to each z in the boundary, it associates a measure. And for our talk, it's a positive bounded Borel measure here for the talk. I mean, more general things can be done. And we assume one continuity condition, so the mapping z from the boundary to this real number is a continuous function whenever f is a bounded measurable function on omega bar. Okay. So now this is the assumption, nothing more. And now the operator can be defined. So it depends on beta and on mu. Beta and mu define these boundary conditions. So the domain consists of all functions in Sobolev space, continuous, such that the Laplacian of u is again a continuous function. And now the boundary condition. The normal derivative plus beta z u of z at the boundary, you see, this z is the boundary, z almost every on boundary, is equal to u and mu z applied to u. Mu z is a measure on omega bar. Z is only on the boundary, but mu z is a measure on omega bar. And this is applied to u. Okay, and then Laplacian, the operator is just the Laplacian. So these are these non-local boundary conditions. So what it does is the following. You tell, I mean, in terms of probability, you have the omega, and the Brownian motion reaches the boundary at a point z, and then you have to tell him what to do. And then it goes back to the interior with this distribution, probability distribution, mu of z. Okay, and then the result is this operator generates a positive holomorphic semigroup and on C omega bar. And now, where does this positivity improving come in? Well, it comes in. What I told you before will be needed for studying this semigroup. It comes in for the asymptotic behavior. And here is the result. So we assume, well, this measure is positive, so we assume that the measure, the amount of the measure of omega bar is exactly this beta, which is given at the boundary. And then we show there exists a measure, again, rho, which is strictly positive, such that T converges asymptotic, exponentially fast to a rank 1 projection. And the rank 1 projection is this. So to F, we apply integral F omega bar, the 1 function. And well, if you know the semigroup theory, positive semigroups, then you know you need somewhere this irreducibility or positivity improving result. And this semigroup here with a mu is difficult to describe, but we have a domination property. It is above the semigroup with Robin boundary conditions. And this we had studied, and we had proven a positivity improving. Now, this result, you see, is older than this recent study with Tom de Elst, Jochen, and so on. So if you look at the paper we published in the Proceedings of a Japanese Mathematical Society, there we assume that this semigroup is irreducible because we didn't know to prove it. We needed irreducibility on C omega bar. And as a paper, this is a hypothesis. But now we need the hypothesis is always true. We don't need any more, it's no longer a condition. Well, I finish my talk. I just should say, all what I said can be done for elliptic operators. So we may replace the Laplacian by elliptic operator in divergence form. So an expression like this, we need this symmetry for the case of the Dirichlet to Neumann operator, and we need also some regularity on the coefficients in the case of the Dirichlet for Neumann operator. In the other case of Robin, nothing of such conditions, of such regularity conditions is needed. They can be just arbitrary measurable coefficients, and they may be also first order coefficients. The result on Robin remains true, and also the last result on the non-local boundary conditions remains true in such a general context. Many thanks for the attention.
Yeah, thank you very much, Wolfgang, for your very interesting talk. So we're open for questions now. Please. Does anybody have a question?
I know a very good question.
I too.
Because you see, I go back to the Dirichlet to Neumann, which was now a long, important subject. And there's a very natural question. I mean, well, we proved we have a C0 semigroup on this space C delta omega, the boundary. Now, is this semigroup holomorphic? Of course, this is a very natural question. And well, the answer is we don't know in this general context, but there is ter Elst and Urbaz. They have a recent paper in the Journal of Evolution Equations, and they prove holomorphy if the boundary, I mean, if omega has C1 plus epsilon boundary. So Lipschitz is unknown so far, but for C1 plus epsilon boundary is, they prove holomorphic. And okay, I mean, this is not proved via Stewart-Masuda technique. It's proved by kernels. And they show, I mean, they use this kernel, this continuous kernel we have established, but they show estimates for these kernels, and they show Poisson estimates. Okay, this is not Gaussian estimates, but it's Poisson estimates, which are true for these kernels. I would not be able to write them down now, but I could write down Gaussian estimates, and if you take the square root of Gaussian estimates, you have Poisson estimates. So the directly to Neumann operator is a little bit like the square root of the Laplace-Beltrami operator. And it is true, so you get these Poisson estimates, at least if you have a little bit more regularity. Okay, so this is some further information, but you might have more interesting questions.
I have a question, if I may ask it.
Please go ahead.
Wolfgang, I remember that several years ago, when we talked, you said that there are no other Banach spaces except for Hilbert spaces. So I would like to ask you, what made you think about the space of continuous functions? Of course.
This is true that I said this.
Yeah, you did. And the other part of the question is, where did this, I mean, in which paper did you publish this result about the third power of the operator T being represented by a continuous kernel?
Oh, this is Journal of Integral Equations and Operator Theory. So the title of the journal is exactly what fits to this.
Journal of Integral Equations and what? Okay, thank you.
Just a second, I can. No.
So Wolfgang, you're lucky that I haven't heard this when you said there are only Hilbert spaces.
Well, you see, I must say, I'm sometimes saying shocking things. This was certainly when we worked on forms and
yes, yes,
and this is so efficient. But a long time ago, I gave a talk, and this was called "Against the Dictatorship of Hilbert Space." So you can also cite this, Adam, if you want.
So may I ask another question? At the very end, you had those non-local boundary conditions, right?
Yes.
And you said, in order to get the asymptotics, you need the Robert-Laplace operator to be irreducible.
Yes. Well, I mean, we need that the semigroup itself is irreducible, but the mu, yeah. This perturbation.
But why do you need this? Why do you need the irreducibility?
Well, to prove that it converges to a rank 1 operator.
So in order for the limit operator to have rank 1, right? Because you always get convergence.
I mean, okay, this is this Frobenius theory. Well, one version of it. I mean, we can probably can't use it directly. I don't remember exactly, but we know, for instance, if we have a holomorphic positive semigroup which is irreducible, and say has compact resolvent, I mean, then it converges to a rank 1 operator if the first eigenvalue is 0.
But that's also true without.
And of course, you see this condition here, this makes sure that the first eigenvalue is 0.
Yeah.
And now the irreducibility, this is to make sure that it's converged to a rank 1 operator. Okay, probably one could otherwise prove that it goes to a finite rank operator. Yeah, this is true. Even stated in the theory, in the paper. Yeah, to a finite rank is clear, but rank 1. So an equilibrium, we want an equilibrium.
Okay, great. Further questions?
I would have a question.
Please, Alex.
May you go to the last slide?
Yeah. This one?
Yes, exactly. Are there any results if you employ drift terms in your differential operator?
I mean, so in the case of Robin boundary conditions, I mean, I had 3 examples, right? So I had the example of the first and the last, so non-local and Robin. Robin local and non-local. So for the 2 Robins, we need only AIG in L infinity, and there may be also BG and CG in L infinity. So drift terms. This is true. For directly to Norman, it's more difficult. We just didn't study the case of drift terms. We wanted a self-adjoint situation. So I don't know, but it was just a choice. It was difficult enough, and was a choice to do. And we needed also some regularity, so we could not do it for L infinity. It's very technical, this proof.
Great.
Does this answer the question, or? Okay.
Yes.
Are there further questions?
Yes. Could you please go back to the third application?
Third application. Okay.
It's just a very quick question of understanding.
Yeah.
It's a very interesting talk. Thank you.
This was maybe.
It was rather at the beginning.
I found it right away.
Yes. To the
semilinear elliptic problem.
Yeah, I think there's a step where I missed an argument on the next slide, I think.
Okay.
Somewhere in the proof. Yes, so how did you get the minus in the second line? So you started with AU is equal to U times 1 minus U.
Maybe there's a...
And then I don't quite see how you get to the next line. So I would ask you to explain that again, please.
Okay. So this is a plus.
Okay. that also answers my question.
And then we have to check whether this is true. You see, we have A, and here the U is positive, and this is to be larger. And now this was on. Okay, this was in the beginning. You see, in the beginning, I had this here, and there was. The larger one was first and then smaller. I think it's correct, so I hope so.
Okay, thank you.
Well, thank you very much. This was just a misprint. Another one, sorry.
Great, thank you. Are there more questions? So we have maybe 3 minutes left.
Corrections also.
Questions and corrections are welcome.
Okay, I have one question, or maybe even 2. So thank you for a really nice talk. First of all, I really enjoyed it. Actually, Johan already started it, and I was not really sure with these connections with irreducibility. So if a semigroup is irreducible, isn't then automatically this positive improving property satisfied?
Yes, if it is holomorphic.
Holomorphic, it was missing. Okay, yes.
Otherwise, no.
Okay, yes.
No.
Yes.
If it's holomorphic, and of course, it is irreducibility in C omega bar.
In C omega bar, yeah.
Because in L2, it would be much weaker. It would only mean that the first eigenvector is larger or equal than 0 almost everywhere.
Of course.
Here we need on omega bar everywhere, so we need irreducibility in C omega bar.
Yeah. Okay, this is stronger.
The groups are all holomorphic, so we get this automatically.
Yeah, sorry. Yeah, I will link this.
But this is this other paper with Jochen, where we have more general situation with the same result.
Okay, thank you. I have to check this. Yes.
Okay.
And another question. So you told us about this kernel, the continuous kernel, semigroups with continuous kernel, and then there was this positivity improving property that follows somehow from that. Yeah. Is there any other property that would also maybe follow from this continuous kernel property?
This is a good question. Nothing comes to my mind, but I just know a lot of situations where in papers this is assumed, or maybe there are many results on Hölder continuity of kernels, because but there you need much more regularity on the coefficients. For instance, in the context of Schrödinger semigroups, but also for elliptic operators. I mean, there are people like there are many results of this kind, and it is true. I don't know, and I should look at these papers how they use continuity. Yeah, it's a good question whether this has more consequences.
Okay, thank you.
Great, wonderful. So it's 11 o'clock now. So let us thank Wolfgang Arendt again for his very interesting talk. Thank you.